Today we are going to learn about Bayesian optimization, a modern approach to hyperparameter tuning. You will discover how to implement Bayesian optimization to efficiently explore parameter spaces and improve model performance.
Welcome to our exploration of Bayesian optimization, a cutting-edge approach to hyperparameter tuning that has become indispensable in machine learning. In this video, we'll delve into the intricacies of Bayesian optimization, understand its pivotal role in efficiently navigating the parameter space, and explore how it can significantly impact the performance of complex models. By the end, you'll be equipped with the knowledge to implement this sophisticated method and enhance your model's efficiency and accuracy. Let's get started on this exciting journey.
Bayesian optimization is a powerful tool used to optimize complex functions that are expensive to evaluate. At its core, it involves building a probabilistic model of the function you want to optimize and using this model to make decisions about where to evaluate the function next. This method is particularly effective in machine learning for tuning hyperparameters, where traditional methods like grid search or random search fall short due to their inefficiency and high computational cost. Bayesian optimization leverages the Bayesian statistical approach, which combines prior knowledge with observed data to make predictions. This technique is especially useful in scenarios where each function evaluation is costly, such as training a neural network. By intelligently selecting the most promising hyperparameters to evaluate, Bayesian optimization can significantly reduce the time and resources required to find optimal settings, making it a valuable tool in any data scientist's toolbox.
The advantages of Bayesian optimization are numerous, particularly when compared to traditional methods. One of its greatest strengths is its efficiency in exploring the parameter space. By using a probabilistic model, it can predict which areas of the space are likely to yield the best results, thus focusing computational resources where they matter most. This leads to a significant reduction in computational cost, as fewer evaluations are needed to find an optimal solution. Additionally, Bayesian optimization is highly scalable and can be applied to models with a large number of parameters, which is often the case in deep learning. Its flexibility means that it can be used across various domains and types of models, from simple regression to complex neural networks. Overall, the performance gains achieved through Bayesian optimization can be substantial, making it a preferred choice for many practitioners in the field. Setting up Bayesian optimization in Python is a straightforward process, thanks to several robust libraries designed to facilitate this task. Libraries such as scikit-optimize, popt, and hyperopt offer comprehensive tools for implementing Bayesian optimization. To begin, one must install the chosen library and import the necessary modules. A typical setup involves defining the objective function, specifying the parameter space, and initializing the optimizer. Scikit-optimize, for example, provides a simple API with functions like gp_minimize to perform the optimization. It's crucial to correctly define the bounds of the parameters and any constraints to ensure meaningful results. An example code snippet might involve setting up a Gaussian process model and using it to suggest new hyperparameters to evaluate. Common pitfalls include improper specification of parameter bounds and neglecting to account for stochasticity in model training. By following best practices and utilizing the powerful features of these libraries, one can effectively implement Bayesian optimization to enhance model performance. Acquisition functions are a crucial component of Bayesian optimization, guiding the decision of where to sample next. They strike a balance between exploring new areas of the parameter space and exploiting known promising regions. Common types of acquisition functions include probability of improvement, pi, expected improvement, a, upper confidence bound, UCB. Each has its strengths and suitable scenarios. Pi focuses on areas with a high probability of improving the current best solution, while A weighs potential improvement against uncertainty, making it versatile. UCB considers both the mean and variance of predictions, lending itself well to scenarios where uncertainty is significant. The choice of acquisition function can significantly impact the optimization process, affecting both convergence speed and the likelihood of finding a global optimum. Understanding the nuances of each function and aligning them with the problem at hand is key to leveraging Bayesian optimization effectively.
Gaussian processes, GPs, are the backbone of Bayesian optimization, providing a powerful framework for building probabilistic models of the function to be optimized. They offer a flexible and expressive way to model complex, nonlinear functions by defining a distribution over possible functions. The strength of GPs lies in their ability to provide not just point predictions but also uncertainty estimates, which are crucial for the exploration-exploitation trade-off in Bayesian optimization. Implementing GPs involves specifying a kernel function, which defines the similarity between different points in the parameter space. Common choices include the radial basis function, RBF, kernel and the matron kernel, each with its own characteristics and suitability for different types of data. The predictive power of GPs allows for accurate modeling even with sparse data, making them ideal for high-dimensional spaces where data is expensive to obtain. Understanding how to effectively integrate GPs into the optimization process is essential for harnessing the full potential of Bayesian optimization.
Bayesian optimization stands out when compared to traditional methods like grid search and random search, particularly in its efficiency and scalability. Grid search involves exhaustively evaluating all combinations of parameters, which becomes computationally prohibitive as the number of parameters increases. Random search, while more efficient, still lacks the intelligence to focus on promising areas of the parameter space. Bayesian optimization, in contrast, uses a probabilistic model to guide the search process, allowing it to efficiently hone in on optimal solutions with fewer evaluations. This makes it particularly suitable for high-dimensional spaces and complex models where each evaluation is costly. Real-world scenarios often demonstrate that Bayesian optimization can achieve superior performance in a fraction of the time required by grid or random search. Its ability to adaptively explore the parameter space and focus computational resources effectively gives it a distinct advantage, making it a powerful tool for practitioners aiming to optimize model performance. The exploration-exploitation trade-off is a fundamental concept in Bayesian optimization, involving the balance between exploring new areas of the parameter space and exploiting known promising regions. Effective management of this trade-off is key to achieving optimal optimization results. Strategies for balancing exploration and exploitation include adjusting the parameters of the acquisition function and integrating uncertainty estimates from the probabilistic model. For instance, an acquisition function like expected improvement can be tuned to focus more on exploration by amplifying the uncertainty component. The impact of these trade-offs is significant, as too much exploration can lead to inefficiency, while too much exploitation may cause the optimizer to get stuck in local optima. By carefully managing these aspects, practitioners can enhance the effectiveness of Bayesian optimization and improve the likelihood of finding a global optimum. Understanding the role of uncertainty estimation and how to adjust exploration parameters is crucial for optimizing complex models effectively.
To illustrate the power of Bayesian optimization, let's consider a practical example of hyperparameter tuning in a neural network. Suppose we have a neural network model for image classification, and we want to optimize hyperparameters like learning rate, batch size, and the number of hidden layers. The first step is to define the parameter space, setting appropriate bounds and constraints for each hyperparameter. Using a library like scikit-optimize, we can apply Bayesian optimization to this parameter space, leveraging an acquisition function to guide the search. As the optimization process unfolds, the probabilistic model updates its predictions based on the results of each evaluation, allowing it to focus on the most promising regions of the parameter space. Once the optimization is complete, we can evaluate the results by comparing the performance of the tuned model against a baseline. In many cases, Bayesian optimization leads to significant improvements in accuracy and efficiency, demonstrating its efficacy in real-world applications. By understanding this process and applying it to neural networks, practitioners can achieve enhanced model performance and greater insights into the optimization landscape.
Implementing Bayesian optimization effectively requires adherence to several best practices that ensure robust and meaningful results. Firstly, selecting the right library is crucial, as different libraries offer varying features and capabilities. It's important to define a clear objective for the optimization process, ensuring that the function to be optimized aligns with the desired outcome. Setting realistic parameter bounds and constraints is essential for avoiding irrelevant or infeasible regions of the parameter space. Monitoring the optimization process allows for timely adjustments and refinements, enhancing the efficiency and accuracy of the search. Iterative refinement and learning from previous optimization runs can provide valuable insights and guide future efforts. By following these best practices, practitioners can maximize the potential of Bayesian optimization and achieve superior model performance, making it a vital tool in the data scientist's arsenal. As we conclude our journey through Bayesian optimization, it's clear that this sophisticated method offers unparalleled advantages in hyperparameter tuning and model optimization. By understanding and applying the key concepts we've explored, from acquisition functions to Gaussian processes and the exploration-exploitation trade-off, you can leverage Bayesian optimization to enhance model performance across various domains. Remember, continuous learning and adaptation are integral to mastering this powerful tool. We encourage you to practice, experiment, and explore the vast possibilities that Bayesian optimization offers, equipping you with the skills to tackle complex optimization challenges with confidence.